All right, we are starting chapter 9, and chapter 9 is all acids, bases, and buffers inside of the body. And acids and bases are super important to our body and our ability to maintain homeostasis inside of us. And so we're going to first look at kind of definitions. What are acid bases? How do we characterize them? How do they behave? And then we'll talk about how they work inside of the body. So just a brief introduction. What is an acid and a base, right? Well, we know that there's a scale, and we say on this scale, if you're over here, you're an acid. If you're over here, you're a base. Well, that scale is called the pH scale, and it refers to the level of acidity in a solution. And acidity has to do with how many hydrogen ions are inside of the solution, right? And so we know that life operates under a super strict pH condition, very, very close to pH 7. And if you fluctuate a little too high, a little too low, the body can't handle it, and you can very quickly die. So it's very, very important that we maintain that correct pH range. And the reason why it's so important is because as you change pH, you know, your body is mainly water and proteins, right? And if you change the pH, then proteins are actually going to change their shape, their ability to function. And so if they can't function the way they're supposed to function, your body doesn't work. And so what you'll see is if you test our bodies, you will see that blood, urine, all that kind of stuff contains compounds called buffers. And buffers are there to maintain a certain pH. So our bodies are going to change, right? You're going to exercise. You're exercising, you're actually going to change the pH inside of your body. And so you have to have a buffer that's going to adjust and keep you from going too acidic or going too basic. So we'll talk about buffers in a little bit. I don't remember which section, but we'll get to it. So there was a chemist named Arrhenius, and he's the one who first described what is an acid. And he said that an acid is a substance that when put into water will disassociate. Remember we said disassociate means split up. So it'll produce what are called hydrogen ions in solution when dissolved in water, right? So the presence of those hydrogen ions gives acids their sour taste, like citric acid, right? Citric acid, all kinds of fruits and things like that, taste very sour. And that allows, that's our way of tasting the hydrogen ions, is to say that it's sour. And this property also allows acids to corrode some metals. So then there was a second definition of acids and bases, and it was Bronsted and Lowry who expanded the definition and said, an acid is not just one that produces hydrogen ions, but it's one that donates a proton. Okay, so that is a question. What's the difference between a hydrogen ion and a proton? Well, you know what a proton is. You know it's a subatomic particle, right? So if we talk about hydrogen atoms, if you go look on the periodic table, right, a hydrogen atom, it's going to look like this, right? And it's a 1. And then it has a number down here, 1008. That's the atomic mass. The atomic mass is equal to protons plus neutrons, right? So if it has an atomic mass of 1, what does that tell you? It's the average atomic mass. What does that tell you? It tells you that most hydrogen atoms have no neutrons, right? You have to have a proton. You have to have 1 proton to be hydrogen, but you don't have to have neutrons. That's the definition of an isotope. So most hydrogen atoms, most isotopes of hydrogen have no neutrons. So they contain basically 1 proton, and then we have this extra mass, right? And 1 electron. And so that gives us our 1.008, right? And so if you have a hydrogen ion, that's an atom that has a proton and electron, and it's an ion, so we lose an electron. And so now we're left with, guess what? A proton, and a proton's positively charged. So a proton and a hydrogen ion are the same thing. So proton is equal to hydrogen ion, same thing. So in an aqueous solution, remember aqueous is water, right? And we all know, oops, you'd think we all know the structure of water like this, right? And so we have this partially negative side and this partially positive, right? So this is our partial positive side, this is our partial negative side. So that partial negative charge on our oxygen atom is strongly attracted to this positively charged proton or hydrogen ion, however you want to say it. And so what happens is that the proton and the oxygen atom are actually going to form a covalent bond. And so you're going to end up making what's called the hydronium ion. Now, the hydronium ion is charged, just like an H+. It has the same charge as an H+. So H3O plus has a charge of +1. H+ has a charge of +1, right? So the charge is the same. But what we're just saying is that that hydrogen ion doesn't really exist in that state as just a hydrogen ion because water's there and water is very attracted to it. And so it's going to pick it up and we're going to make a hydronium ion where we actually have 3 hydrogens attached to the water and only 1 lone pair. And that gives this, this substance a positive charge and we call it the hydronium ion. Okay. So that's acids. Now bases. According to Arrhenius, bases are compounds that, when dissolved in water, dissociate to form a metal ion and what's called a hydroxide ion. Hydroxide is OH minus. So most of these bases are in group 1 and group 2 metals, like sodium hydroxide, NaOH, potassium hydroxide, KOH, lithium hydroxide. I think that actually is an L, but it should be lithium hydroxide, and calcium hydroxide, right? Those are all group 1 and group 2 metals in association with this hydroxide ion. So hydroxide bases, if you were to taste them, which you should not, they're bitter. and they also have a very slippery feel to them, but don't touch them because they could damage your skin. So don't, just take my word for it. And so that's the Arrhenius definition, right? Creates an OH minus, a hydroxide ion in solution. But there's also a Bronsted-Lowry definition. And this is the definition we're going to work with quite a bit, is that this base is going to accept a proton. And so what you can see here is, for an example, one substance, NaOH, it's a solid, it's an ionic compound. We have a polyatomic ion and a metal, and we're going to put it in water. And when we put it in water, what's going to happen is it's going to disassociate, and it's going to form our sodium ion and our hydroxide ion, right? And so that hydroxide ion gives it its definition as a base according to the Arrhenius rules. So you got to kind of remember that acids and bases are both present whenever you have an aqueous solution, because water can act either as an acid or a base depending on what it's doing. So let's look at the first example. We have HCl, right? HCl has the hydrogen, right? And so when we put it into water, what's going to happen is you're going to go, whoa, you're going to go from HCl to H plus Cl minus, right? But we said that this doesn't really exist by itself because we have water. So when we have water, what we're going to do is we're going to attach this extra hydrogen onto that water molecule. And that's going to give, and you still do have a lone pair up here, but that's going to give this hydronium ion a positive charge. And then we still have our chloride ion here, which is negatively charged. And so we know that this is a donor, a proton donor, because it donated this hydrogen to water. And we know that water is a base because it accepted the hydrogen ion, right? And so that's our definition of acids and bases. So let's look at another one. This is kind of an opposite example. Here we're looking at ammonia. Ammonia is a base. By definition, you have to know that a base is a hydrogen ion acceptor, which means it's going to gain a hydrogen. How is it going to gain a hydrogen? Well, it's going to take a hydrogen from water. and stick it on right there, right? So you're going to make what's called the ammonium ion, and the ammonium ion has 4 hydrogens, right? This was 1, 2, 3. Now we have 1, 2, 3, 4, and it's now going to have a positive charge. So this one accepted this hydrogen ion right there, and then water gave it up. So water is the donor, and then it creates OH minus in solution, right? Okay, see if I can go on to the next slide. Oh, okay, let's go do some problems. All right, so 9.1, identify if each of the following statements is characteristic of an acid or a base. So has a sour taste. I want you to think citric acid. So this would be acid. Oh, I kind of wanted to do them each in different colors. So we kind of, so acid. So this would be citric acid. Like if you've ever pickled anything, right? You pickle it in vinegar. Vinegar is, the main component of vinegar is acetic acid. Acetic acid, right? You know that pickling stuff is very, very sour. Okay, accepts a proton. What accepts a proton? That would be a base. A base by definition accepts a proton. Produces hydrogen ions in water. So if I put something in water and it produces hydrogen ions like HCl, right, makes H plus and Cl minus, well, that must be that this is an acid. Let me go ahead and erase that, right, acid, okay, is named potassium hydroxide. So most acids are called acids. You'll hear it in their name. And a lot of times when you hear a base, not always, but a lot of times when you hear a base, you'll hear hydroxide. So this is a base, okay? All right, in your own words, explain how a proton and a hydrogen ion represent the same thing. So one proton is 1 P plus, right? That's all it is. So we call that a hydrogen ion. Why? Well, we know a hydrogen atom, right, is equal to 1 proton, 1 electron, and 0 neutrons, right? So, and that's because the atomic mass is equal to 1.008, right? If it were a proton, a neutron, and an electron, it would be like 2.008, but it's not. Okay, so the hydrogen ion is the atom, is the hydrogen atom without the electron, right? It's lost the electron, or it's lost the electron, okay? In each of the following equations, identify the reactant that is the acid, the hydrogen ion donor, and the reactant that is the base, the hydrogen acceptor. So let's look. I kind of like to look at things that look the same from the left to the right. So what I'm going to do is I'm first going to look at water. Now, what does water kind of turn into? Water turns into the hydronium ion. So tell me, what is happening as we go from water to the hydronium ion? Well, I'm accepting, I'm adding another hydrogen on there. So this is my hydrogen acceptor. So what did it have to be to start with if it was going to accept a hydrogen? This has to be the base, okay? Now let's look at HBr, and it goes to, I don't know why that's a superscript. It should be a subscript, Br2, right? Weird. Okay, so HBr, what's happening to it? We're going to lose our hydrogen, right? So if we lose our hydrogen, then we're going to be an acid, because the definition of an acid is our hydrogen ion donor, right? So keep in mind that acceptor, donor, and just kind of see what happens. All right, HCO3 minus plus H2O. Oh, I just like to look at my water. I just like to say, okay, what happens to my water? So here, right, I went from H2O to OH minus. What happened? I lost a hydrogen, right? So this is a hydrogen donor. So my H2O ends up behaving in this case like an acid. So remember how we said water could act as an acid or as a base, either way. Okay, now HCO3, H2CO3. So what happened to get from here to here? Well, I had to accept a hydrogen. I had to be a hydrogen acceptor, right? My hydrogen acceptor is what I call my base. Okay, that's it. All right, y'all have a good rest of your day.